Good. We can continue with your first. Let's try that with knocking. It's like starting lecture. Can you do me a favor and knock the table? So we all know how we start. Thank you. You will learn now about your first real machine learning algorithm. Well, actually, it's not really machine learning, as I would argue, but I will tell you later why. Nevertheless, it is going to be your first algorithm. K-nearest neighbor and the vector space. And you don't have to do that. Can you just raise your hand if you think you are very familiar with the concept of a vector space? Okay, not so many, but we will talk about that in more depth. Yeah, that's okay. So we will use this example, this lecture, and also the following lectures with the students, with this tabular data, where you have your row IDs that represent your students. We know about each student, the student ID, the study time they invested per week, and the average marks and the final salary. And our goal now is to predict this salary for one new student for which the salary is unknown. But we look at this as a classification problem. So we don't want to predict the exact salary. We only want to predict a class. And in this case, the class is medium salary or high salary. Doesn't really matter how we name this. It could also be low salary and high salary. Doesn't matter at all. Any class in machine learning is kind of featureless. It's just like an entity without any unique characteristics. Doesn't matter if you call it high or medium or 0 or 1, at least in this example. So first step, almost always, plot the data. But it will be different from the example I showed to you in the introduction lecture. This time, we plot, you remember maybe just half an hour ago, the example with linear regression, we plotted the target as the Z on the Z axis. This time, the target, medium or high salary, is not directly plotted as an axis, it's plotted as an icon for the instance. So we have only the independent variable on the two axes, the average marks here, the study time here, and then the label Z is directly incorporated into, well, the representation of the instance in the vector space. This is called a vector space because each instance, and we talk about that next lecture in much more detail, is considered a vector. Like student 1 comprises, or is the vector comprising of the two elements x2 and x1. So that would be here. And the red circle then means the student had a medium salary. So we want to know the label for this student, and forget what you learned about linear regression so far. It's a new approach. The core idea of k-nearest neighbor, and again, this is just one of many algorithms. It's just one concept that some person someday developed in the same way as someone had the idea for bubble sort, and someone else had the idea for quick sort. Someone had the idea for k-nearest neighbor a long time ago. And the idea of k-nearest neighbor is that in the vector space, you look at the k, so 2 or 3 or 4 or 5 nearest neighbors, look what class they have, and whatever class appears most often in those neighbors, you assign to the new unknown class. So in case of k equals 3, you look at the k nearest neighbors, that's the very nearest, the second nearest, and the third nearest. You see that 2 out of the 3 classes have high salary. So your best educated guess would be that this student also will have a high salary. That's the basic idea of k-nearest neighbors. I think it's a very intuitive idea that maybe also many of you are already thinking about that, did when I asked you how much will your salary be. You were thinking probably of people who are similar to you in terms of age, clearly in terms of education and job they want to do, maybe in terms of intelligence. Yeah, maybe you have some friends who just graduated already, and maybe some of them are much more intelligent than you, and you know they earn this, and then you think, oh, maybe less. This friend who's like me, more or less, I will earn probably around the same like this person. So that's the basic idea of k-nearest neighbors. Most people apply that all the time in their daily life. More realistically, it probably looks like this, the data. And now we get to your first algorithm. That is the first algorithm. Just a few lines of code. And that is the k-nearest neighbor machine learning algorithm. Have a quick look at that. We talk about that in 2 minutes or in 1 minute. So this example, or this algorithm, I just copied from a book. The book is about document classification. So maybe it's not immediately clear what everything means. So let's go through that together. X, capital X, is a collection of documents. It's written as capital because it's a collection, and it's bold because it's a collection of vectors. Each document is an entity, an instance, and each instance is represented as a vector, whereas each vector is a feature dimension. So you have the documents, you have the labels. So in this case, it would be high income or medium income. And you have X. In the book, X is a search query, I believe. But in this case, it would be our student that we are looking for to predict the salary. Yeah? This here would be X. And then all the instances in here would, so the student would be the not bold small x, and all the other points here are the capital bold X, and the labels are, well, then the crosses and the circles. What we then do is for each instance in the data set, compute the distance between our student in question and all the other students. So the distance between this and this, the distance between here and here, the distance between here and here, and so on and so forth. After we did this for all instances, we compute, or we identify just those k instances where the distance is smallest. And then we return the majority label of those instances as the new label. Super simple, right? You probably could have come up with that yourself if you had thought about that for a while. If you had done that, I don't know, 60 years ago, you would be very famous now. This is a machine learning algorithm because it's applicable to any kind, almost any kind of data. So you don't need any domain knowledge. It doesn't matter if it's students or house prices or pies. You can just use that to classify. It works reasonably well. Do you see any problem here? Like if you were to work in a company and then you say you have a few thousand or maybe 100,000 customers, and you want to use that on a regular basis. Any issues here?
This is not really sponsored by politics. So I do not think it would be their own. Can we distinguish that way? Thank you. It's reasonable. Just
yeah, and of course there's many things like in the concept you can criticize. I rather think now from a computational perspective, like from software architecture, computational perspective. Yeah.
It takes a lot of time to just compute this.
Yeah, exactly. For every prediction you want to make, you have to calculate the distances between the input instance and all the other instances. That takes a lot of memory. So just before we were talking about model-based and memory-based models. This is a memory-based model. You need to load all instances into your memory, which is no problem for a few thousand instances. But let's say you have a normal laptop, you may run already into problems once you reach a few 100,000 or definitely a few million instances in your data set. And a few million is not so much in the machine learning world. Of course, there are many tweaks to improve this and make it faster. But the advantage is, you will see that next lecture, you don't need time to build a model, which also can be very computationally expensive. Maybe you have heard that to train ChatGPT, you need months of training and it costs millions of euros because they have thousands of GPUs running to train the ChatGPT model. Here, you just load your data to the memory and you can make predictions right away. Anyway, just keep that in mind. It requires a lot of memory. It's computationally relatively expensive. But again, a very simple algorithm. I mean, you can just program that with a few lines of code. Even if you were to calculate this yourself or program this yourself, it's just a few additional lines of code. There's no real learning involved here. That's why I'm not so happy to call that a machine learning algorithm. It's rather, again, a heuristic, this assumption that entities that share the same attributes also have the same taste. You may, I mean, further of all, often it works well, also with smaller data sets, so it just works, that's very good. But in some cases, it might not produce ideal results, depending, I don't know, if you use as a feature gender, then you would always assume that all women have the same taste, all men have the same taste, which may be true sometimes, but sometimes maybe not. Yeah, so it's a heuristic that that entities with the same attributes also have the same taste. In this lecture series, we will only talk about binary classification. Binary classification means 1 and 0, or like and dislike, or cat and dog. In the practical world, of course, you typically have multi-class classification, but that's beyond the scope of this lecture. You still use more or less the same algorithms. It's just a bit more complex. Okay, to do this, like to implement this, what do you need to know? If I tell you in the lab session, program this, what would your questions be? Yeah. Yeah, right. What is K? What was the second one? How to calculate the distance. And the third one, not really. That's your third point would be included in how to calculate distance, I think. The third point is how to do this effectively, because otherwise it would be too much computational time most of the time. We will look at the first two questions now. How to choose K, and what is the distance, or what does it mean to be close, how to measure it. So, and we will just talk again about accuracy and how to measure effectiveness. So let's start with that, measuring the effectiveness of a classification algorithm. You have your data set, and you use some of the data points randomly that you chose, 20%, to test your model later on. So What you then would present typically, so this is not specific to kNN, this is specific to any machine learning algorithm. What you then do is present two algorithms against each other, algorithm A, algorithm B. You know the target, what is the actual class, you know the prediction of algorithm A, you know the prediction of algorithm B, and if it's correct or not. And then you just sum it up. And in this case, on average, you have 50% correct predictions. Here you have 8, 1, 2, 3, 4, 5, 6, 7, 8. So algorithm A would be more effective. Very simple. I just want to, you probably know this, but anyway, just to remind you. Okay. How to choose K? K is a hyperparameter. That is something that cannot be learned. There's no right answer to this. It's something that either based on your gut feeling or better based on experimentation, you must choose individually for each data set. So K is something, the ideal K is something that may vary from data set to data set. To illustrate that, if you choose K equals 1, so you classify each data point based on the class of the one nearest neighbor, you would end up with a very scattered landscape. So what that means is, if you were, if here would be a data point, then the K nearest neighbor would be orange. Also, if you would to classify, so if you wouldn't know the class of this point, then the nearest neighbor, this one is orange. So you see here the orange surface. Every point in that orange surface would be classified as orange because then the nearest point is orange. Any point, like if now a new unseen point was here, the nearest neighbor, the one nearest neighbor is here. So a point here would be classified as blue. And you see already, this is very scattered, which is probably not ideal. It's not, I mean, again, it's not that I could say with 100% certainty it's not ideal. You don't know 100% for sure. It depends on how the new data would be distributed, but chances are high it's not good. So here, if you look at the 20 nearest neighbors, you would have a much smoother landscape. But based on this, you could argue that some points are misclassified. Yeah? If you had not this label, you would classify it as orange because all around here is orange, but actually the label is blue. So with K equaling 20, you would have now also if you pick some instances randomly, you would maybe have incorrect predictions, even though in practice this might work better. What if K equals M? M is the number of data points in your data set. Yep. Yeah, it would always be the average. Sorry, if K equals M, I have to think about this myself. Here's some more examples with different classes. So this is the data. And if you would have then a multi-class classifier here with one nearest neighbors or here with 5 nearest neighbors, it would look like this. Coming back to the hyperparameters about K, I said already you cannot learn it. You must try it. So one thing to do is you would take your K nearest neighbors algorithm and try it out with K equals 1, and you would get this result, for instance. And you would try it with 2 and 3 and 4 and 5 and 6 and 7 and so on. And you maybe get this chart. So the K you would choose would be this one, I don't know, around 15. The problem is you don't know always for sure that if this goes down, the accuracy, that it might not go up at some other point. There's no guarantee for that. That's machine learning. I mean, of course, you could try all Ks if the data set is not too big, but yeah, this is also not the only hyperparameter you have to optimize. There are many things you can try out in machine learning. So there's also some smart search strategies. It's of course not necessary to try K equals 1, 2, 3, 4, 5, 6, 7. You can try K equals 1, 5, 10, 20, 50, for instance, depending on how much data points you have. There's some rules of thumb. They don't always work, but if you have nothing better at hand, they might be the best you can do. Something like K should equal the square root of M. And then there's different search strategies, random search, grid search, Bayesian search, and others. This is a research field in its own. It's not trivial to optimize hyperparameters. So there's lots of research on how you can do that with relatively low computational effort. Yeah, this is like a real experiment with 5-fold cross-validation. 5 folds mean every experiment was repeated 5 times. So for every K here, you see around 5 data points. So for K equals 50, one result was here. So the accuracy was around 0.26 something. In this next attempt, it was 0.27 something. The next one was very close, here very close, but here it was 0.29. So, and this is a very realistic outcome. If you repeat the same experiments multiple times, based on how you randomly split your data, for instance, you get different results. And I mean, it is quite a difference. So 0.27 and 0.29. And then the blue line here is the average. So you would choose some K somewhere here. If you had run this experiment only a single time, it could be that the first time maybe K is here. So for this run, you get this K. Then it goes up a little bit here. Then it would go down, then here, then here, then here, then here, then here. So you would choose a different K. So it makes sense often to repeat your experiments and average the results to get a reliable estimate. Very important, and I mentioned that every time in the lecture and the exam, this is often gotten wrong, hyperparameter tuning. So tuning refers to finding the optimal hyperparameter, the optimal K. It's different from learning parameters for a model like linear regression. We will see that in the next lecture as well, when we learn parameters to get the optimal prediction with linear regression. Those parameters in linear regression are being learned. Hyperparameters are only found through trial and error or intelligent search strategies. Okay. So what K should we choose? The one that performs best on some training or on some test data. The next question is, what is distance and how to measure it? So we have our instance xi, and we want to measure the distance to a different point xp. So we need to know the distance between xi, but it's not consistent. So here I wrote x and xi. Here it's xi and xp. Well, I think you understand what it is supposed to be. And for this, we need the vector space. We represent each instance as a vector. And all vectors together are the matrix of instances. So this is our matrix of our data. This would be instance 1 comprising of feature 1, feature 2, or feature j, and feature n. This is instance 2, comprising of feature 1, feature j, and feature n. So all these elements together form the vector, the instance vector xi. Or here, that's the first instance, x1 and xm. It's the mth instance in the data set. And then we have our labels, whereas label 1 specifies the right answer for here, instance 1. We represent now each of these instances in the vector space. So if we have an n-dimensional, if we have n features, it means we have an n-dimensional vector space. Each feature represents a dimension. So this could be the study time, this could be the average marks. We ignore now this, let's assume it's just 2 features. That means we have 2 dimensions. Dimension 1, for instance, the study time. Dimension 2, for instance, the average marks. And then instance 1 would be plotted here in the feature space. Instance 2 here, and instance 3 here. We could equally well see that as points. That's the same. Mathematically, a point is not a vector, but in machine learning, we are not so strict. It doesn't matter how you term this. So just going back. So feature 1, instance 1 or instance A just has the coordinates x11 and x12. That's our document A or student A and student B and student C. Yeah, I think that's what I said. Let me see. Did I miss something you can remember? All instances, all data points are vectors in the vector space. Each feature or attribute equals 1 dimension in the feature space. Yeah. So let's look at a simple example. We only have 2 instances in our feature space, x1 and x2, each with 2 features, and we want to measure the distance. And there's different ways of measuring distance between vectors, between points. The most common one is the Euclidean distance, also L2 norm. That's what intuitively people would consider the distance. It's like the direct connection between the 2 dots, 2 points. So that's the Euclidean distance, just a straight line between the 2 points. And we can calculate that quite easily, looking at one point first and the distance from the origin. You maybe see this is almost a rectangular triangle. So the length of a vector is given, is this, or this is just how you write the length or the magnitude of a vector. And here you have the triangle, and you may remember from high school, if you want to calculate how long this is, and you have this length and you have this length, you just take the square of each part, add it, and then take the square root. So a Quadrat plus b Quadrat gleich c Quadrat. A squared plus b squared gleich c squared from high school, Pythagoras. And then the square root to get the single length. More general, we are typically not talking about 2-dimensional vector spaces, but n-dimensional vector spaces, but it's the same. You just square all the individual terms, sum them up, and take the square root of this to calculate the distance from the origin. Now, we don't want the distance from the origin. We want the distance between 2 points, but it's pretty much the same. So this is what is given. We have given this, and this coordinates. That's the features, the attributes. So here, 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 and here. And we have again a triangle, a rectangular triangle here that we can calculate. We can calculate this length as x11 minus x12. Sorry, x11 minus x21, and here x22 minus x12. So if we square this and we square this and take the square root, we just have the distance in the vector space. And again, for an n-dimensional vector space, it's the same. You just take all the differences between all the dimensions, square them, sum them up, and take the square root. A bit more compressedly written is this way, like these double pipes. That refers to the L2 norm. You must remember that. Yeah, we will not do that. We can do that in one of the lab sessions. Or I go, okay, I go through it very. No, we will skip that. Okay, so back to the distance for kNN. What is the distance? How to calculate it? We just covered that. Now the next part is comparing the instances. And about the complexity of a naive kNN. Important are the number of nearest neighbors, the number of features, and the number of instances. And then you have, but the number of nearest neighbors is relatively not important. So that is the time complexity, and that is the space complexity. So you see, it's very expensive. There's many ways of improving this, which we will not cover in this lecture series, but if you're interested in learning about this, it's also relatively simple. Things like a KD tree or a ball tree, they do some intermediate steps and they get much more efficient. They have, it's still not perfectly efficient, but better. Let's say it's much better. Log M here, or N times log M. That is kNN, but I just want to ask you one thing. What's wrong here? That's what I showed you in the beginning of the lecture. Some of you know this already from the SIS lecture probably, but anyway, yeah.
The axes are like scaled. It's maybe
yeah.
This is between one.
Yes.
What's one divide.
Exactly. Absolutely right. The scale here is not correct. And I hope you all saw this already. If not, I can recommend to you only always check the axis, the X and Y axis. If you see, it doesn't matter if it's a newspaper, if it's a lecture from a professor, because people do mistakes, sometimes on purpose, if they want to transport a certain message, sometimes just because it's a mistake. So what you should have seen already in the beginning is here the scale ranges from 1 to 4. Here it ranges from 0 to 70. But like the physical space on the screen is the same. If you would have, I mean, there's one other issue, and that is that marks are not really linear. Like a 5.0 is, you would argue that the distance between a 4.0 and a 5 should be much, much larger than between 3 and 4, because a 5 is a fail. That's like much, much worse, but that's just a side note. So if you would scale this properly, where the units have the same physical amount on the screen, it would look like this. If the marks also range from 0 to 70 or to 80. So it's the same like the study time. This has nothing to do with machine learning, really. It's just like a bit about critical thinking. that you should apply when you see my lectures, because I also do mistakes. This is kind of intentional, but I'm sure there's more mistakes on some slides. Yeah, so if you think that some slides are not correct, please post in the forum. And if you read newspapers, always apply critical thinking. Yeah, there's a few. kNN is very old. Consequently, there's many improvements and advancements in that area. Instead of a fixed size k, you could use a radius. If you have a very sparse space, you maybe don't want to use k nearest neighbors because maybe the 10th neighbor is quite far away. So you only want to use data points close to your input point. You can weight the distance, that if a data point is further away than another, then that data point that is further away should be weighted less strongly. You can reduce dimensionality of points and many things more. If you're interested in that, there's many papers on this. You can use k nearest neighbor also for regression. It's typically a classification algorithm, but you could equally use it for regression. So if you have the 3 k nearest neighbors, you just take the average of the numbers and assign that number to this instance. Again, you may want to weight based on the distance, whatever. I think if you look at this, where will kNN work better? Question is probably too easy, right? Here it will work much better. The more separated the labels are, the better kNN works. There's many distance metrics more that I will show to you on the next slide very briefly. But a good metric in kNN, a good distance metric, is a metric that where the points in the vector space are then kind of grouped for the instances, so that you could try out different distance metrics. And if one metric is giving you something like this and another distance or another transformation of features is giving you something like this, that would be better. Let's go quickly through other distance measures. So I just told you about the L2 Euclidean distance. Another common one is the L1 norm. That's the Manhattan distance, where the distance is simply calculated as the sum of the differences of each feature. You don't square anything here. You just take the difference between feature 1 and add the difference between features 2 and the difference between feature 3. It's called Manhattan distance because in Manhattan or taxicab distance, you cannot go the direct way. That would be here. That's the Euclidean distance, the green one. In Manhattan, where you have all these blocks of streets like this and this, if you want to travel from point A to B, you can travel like this, or you can travel like this. It's the same distance. It's longer than the direct distance, direct in terms of like Luftlinie in German. This can sometimes yield in better results than Euclidean distance if you use this distance measure. To illustrate this, what it means, suppose you have 2 persons and the features you have is the time for swimming and the time for running. Then you could calculate the L1 distance and the L2 distance, which in this case are the same. But the L2 distance is kind of a radius, like a circle, and the L1 distance is like a square. So here, and here, L2 and L1 would be the same, but any point here or here, the L1 distance would be larger. If we look at this, here the L2 distance is 2 everywhere, but here the L1 distance is already 2. So going to here means L1 would be larger than 2. So if I see this correctly, and if I remember correctly, let me think. The L2 distance can never be smaller than the L1 distance. Does that sound about right? There's just some more examples. So probably not. The L1 distance makes sense intuitively, I believe, when features are very different. One example is color. In image classification, or whenever you do something with images, often the L1 distance is used. You can imagine if you have, let's say, 3 dots here, 1 point here, and then you have a point here and a point here. The Euclidean distance, let's say roughly it's the same. This distance, let's say it's the same as this distance. But comparing this point and this point, only the red value changed. Comparing this point and this point, 2 values changed, the blue value and the green value. So the L1 norm punishes kind of changes in 2 variables over a change in 1 variable. And that, if you think about similarities, I think it's not always the case, but you hopefully would agree that sometimes it sounds plausible that if you want a point that is similar to this, then some point where only 1 color dimension changed in a tendency is more similar than a point where 2 color dimensions changed. This is the Minkowski distance. That's a general form of distance measures. So that's the formula, just to subtract, take the absolute value of the subtraction of 2 features and take it to the power of q, and then sum this up and take the square root, the q's square root. So if q equals 1, then this becomes the Manhattan distance. If q equals 2, this becomes the Euclidean distance. And this goes to infinity, which is called the chessboard distance, which is not relevant for us now, but at least you have heard about this. Yeah, maybe look at this at home. It's a question to think about. Which metric is best in machine learning? If I ask a question like this, the answer almost always is depends. If I ask you which k is best, the answer is it depends. Which metric is best? It depends. Which algorithm is best? It depends. Almost always. There's thousands of research papers looking into comparing and proposing new metrics, distance metrics. Sometimes there are some areas, like I said, with image, when you work with images, L1 tends to be better, but it's not always the case. Yeah. So again, that's the kNN algorithm, and it concludes this lecture. If you want to see more details on this, also on some like how we can tweak the performance, I would recommend here this video and some lecture notes. Any questions? Then congratulations, you have the first idea of machine learning. I hope I see you next week. Thank you very much.